So hello everyone. In last class we have studied about formation of carbocation, and in formation of carbocation we have studied two methods of formation of carbocation. First is by heterolysis of covalent bond, and second is by reaction of electrophile with olefinic bond. Olefinic bond means pi bond. Now we also studied about the leaving tendency of leaving group. So we have studied that leaving tendency of leaving group is directly proportional to stability of Lg minus, or basic strength of inversely proportional to basic strength of leaving group. So today we will study for reaction of carbocation. So carbocation shows three types of reaction: rearrangement, combination, and elimination. So now we have seen like different types of organic reaction in the first class of reaction mechanism. So we have seen this type of reaction also. This is called multi-step reaction. So we have seen this part. In formation of carbocation, we have studied this part, that reactant is converting into intermediate. So intermediate is carbocation. Now here in this class we will study intermediate converting into intermediate. So we will study this part in rearrangement of carbocation. So here we will see that why intermediate and how intermediate is converting into another intermediate. Then intermediate to product we will study later. So we will see this in rearrangement. So what is rearrangement? So carbocation usually show rearrangement to attain higher stability. So I will take one example of carbocation. See, suppose this is the carbocation here. C, CH2 plus. Here three groups are there: P, Q, R. Now, if this carbocation rearrange itself on this carbocation, on this carbon, and this carbocation is more stable than this carbocation, then it will go into the rearrangement. So suppose after rearrangement, if this carbocation is coming on this carbon, now this it will form this product. Now if this is more stable than this one, then this carbocation will go into rearrangement. Only case when this is more stable than this one. Now how this rearrangement takes place? Suppose in this case this P is migrating on this carbon. So how this P will migrate on this carbon? So if here more stable carbocation is forming, so this P will start taking its electron. If this P will start taking its electron, delta negative charge will appear on the P and delta positive charge will appear on this carbon. Now this delta negative charge and this positive charge on this carbon, they will interact with each other. So if they will interact with each other, so this transition state will form delta negative on this P, delta positive on this carbon. This is Q, this is R, and this is CH2. So if this is carbon number 1 and this is carbon number 2, 1-2 shift is taking place. This P is going from 2 to 1 carbon. This is called 1-2 shift reaction. This is called 1-2 shift. So why this P is going from 2 to 1? Because more stable carbocation is forming on the 2. That's why this rearrangement is taking place. This is called 1-2 shift reaction. Now, when rearrangement takes place, when more stable carbocations form, then only rearrangement takes place. If more stable carbocation is not forming, then no rearrangement will take place. So, we see. You can here. Suppose we have this carbocation here. Now, if this is carbon number 1 and this is carbon number 2, with respect to this carbon, this is carbon number 2. With respect to this carbon, this is carbon number 2. Now, in this case, this carbocation will rearrange itself to that carbon, which will give more stable carbocation. Suppose if this carbocation is rearranged to this carbon, and this carbon is most stable carbocation, then it will rearrange itself to this carbon. Understand? Now we'll write some point in notes. first is rearrangement only takes place when more stable carbocation form. If this is stable, if this carbocation is stable, this will be more stable. So rearrangement only takes place when more stable carbocation form. Second is a 1-2 shift. In this case, 1-2 shift takes place. Third, see, this one is a 3-member cyclic transition state. Na? 1, 2, 3. So 3-member cyclic transition state formed during rearrangement. 3-member cyclic transition state formed during rearrangement. Transition state formed. Now, fourth point, most important point. Now, if this is the carbocation, this is P, this is Q, and this is R. So between P, Q, and R, which will migrate on this CH2, so that this carbocation, this positive charge will come on this carbon. So factors for migrating. Factors which affect migrating aptitude. So first will be, see, bond strength. This will depend, migrating aptitude of this PQR will depend on bond strength. If more bond strength will be there, so it's less likely to be get migrated. So it should be less bond strength. Second is, now this P is moving to positive charge. So if between P, Q and R, which is more electron density, that will more likely to migrate on this carbon, because this is positive charge, this will need electron density. So second is electron density. More electron density, it is more likely to be migrate. More electron density. And third one, less steric factor. So if steric repulsion is less, then it will be more likely to be migrate. So steric factor, less steric factor. So these three factors affect the migration. We will combine all these three factors and see which will be good for migrating. So factors which affect migration is less bond strength. If bond strength is less, then it is easy for migration between P, Q and R. Then more electron density. If more electron density is present, then this is positive charge and it will easy to migrate if it has more electron density. And then a steric factor. So steric factor should be less. Now all these three factors will not be found in single compound. So we'll see the migrating aptitude order. So migrating aptitude order is very rare to found all these three in a single compound. So we'll see migrating aptitude order. So we compare between hydrogen and aromatic compound and alkyl group. So migrating aptitude order will be this. Hydrogen, if hydrogen is present, hydrogen will migrate first, then aromatic compounds, then alkyl group. Second, you will see between hydrogen, deuterium and tritium. Now, you know hydrogen has less bond strength than deuterium and deuterium has less bond strength than tritium. So migrating aptitude in this case will be hydrogen, deuterium and tritium. Third, if you have to compare between the aromatic compounds, between aromatic compounds, if you have to compare, which will migrate first? which one has more magnetic aptitude? Now see, this one, due to plus R effect, it has more electron density, and here it has plus H effect. So between plus R and plus H, you know that plus R dominates. So this has more electron density. So this has more magnetic aptitude. Now between this and this has more electron density. So this has more magnetic aptitude. But if you see this case, now you will say, okay, this case, this has 2 plus R effect. This 2 OCS3 group has 2 plus R effect. But we have to also see a steric factor. In this case, due to this 2 large OCS3 group, more steric factor will be there. So it has least magnetic aptitude due to a steric factor. You have to remember this magnetic aptitude order, very important. Now we'll see the fourth one. Now between 3° alkyl group or 3° carbon, fourth one, (2° carbon, (1° carbon, and next this one. So if we compare magnetic aptitude between these 4 groups, so it will be like this. First 3° carbon, then 2° carbon, then this, then this. Why this is the magnetic aptitude order? When we do example, we will see this. What is the reason? So now we see fifth one. Larger alkyl group. If larger alkyl group is present, so they migrate first. They have more migrating aptitude. Larger alkyl group has more migrating aptitude. This you have to remember, migrating aptitude order, very important. Next we will do some examples. So first example is, we have to tell if in this case rearrangement is possible or not. If rearrangement is possible, so how many number of 1,2 shift will take place? Number of 1,2 shift. Also you have to tell if rearrangement is taking place in this compound or not. Second, you have to tell in this case also if rearrangement will take place or not. Third, in this case also if rearrangement is taking place or not. Fourth, in this case also if rearrangement is taking place or not. If rearrangement is taking place, so how many 1,2 shift will be possible and which group is migrating, that also you have to tell. So if you see in this case, for rearrangement we need 2 carbon, so there is no carbon, there is only single carbon, so there is no rearrangement possible in this case. No rearrangement, no 1,2 shift. Now if you see this carbon, if this is carbon number 1 and this is carbon number 2, so if we do the rearrangement, now this product will form CH2 plus and CH3, and both are same only, they have same stability, and rearrangement will only take place when more stable carbocation will form. So in this case they have same stability, so no rearrangement will take place, no rearrangement. Now tell me in this case, Now this has positive charge. Now this is carbon number 1, this is carbon number 2, and here also this is carbon number 2. So if you shift this positive charge here, it will become less stable. Now in this case, more number of alpha hydrogen is present. On this carbocation there are 6 alpha hydrogen. If you move this carbocation, rearrange this carbocation on this carbon number 2, it will have no like only 2 alpha hydrogen. That will be less stable. Na? So no rearrangement will take place. If you do the rearrangement in this case, if you suppose we are migrating this hydrogen, one hydrogen is present now, this hydrogen will migrate on this carbon, and this product will form CH3, CH2 and CH2 plus. So in this case number of alpha hydrogen is 6, and in this case number of alpha hydrogen is 2 only. This is less stable, na? Less stable. So no rearrangement will take place. No rearrangement will take place. No 1 to shift will take place. Now see this one. If this is carbon number 1 and this is carbon number 2. Now in this case, if you do 1 to shift, if this hydrogen present on this carbon is shifting on this carbon, sorry, 1 to shift will take place, no? So from 2 this hydrogen present on this carbon will shift on this carbon, and now the carbocation form will be CH3, CH plus and CH2, CH3. Now in this case number of alpha hydrogen is 2 only, and here number of alpha hydrogen is 6. So this is more stable, na? This is more stable. So in this case rearrangement will take place, and how many 1 to shift is taking place? Only 1. So one hydrogen is one hydride shift is taking place in this case. So in this case rearrangement will take place. In all these 3 cases no rearrangement possible. Rearrangement only possible when more stable carbocation is forming. Now I will give you some example and you have to do by yourself. You have to tell if rearrangement is possible or not, and if rearrangement is taking place, so how many 1 to shift will take place in that case. So I am giving you some example. 4th, 5th. In this case you have to tell rearrangement is possible or not. 6th, 7th, 8th, now tell me in this case rearrangement will take place or not. First you pause the video and do it by yourself, then only see the solution. So we take this carbon as a carbon number 1, this carbon is a carbon number 2. So now on this carbon number 2, hydrogen is present, and if this hydrogen will shift here, if this hydrogen will migrate here, and carbocation form will be this. Now if you see in this case number of alpha hydrogen is 3, 3, 6, 9, and here number of alpha hydrogen is 1 only. So this is more stable. So rearrangement will take place. So how many 1 to shift is taking place? Only 1 to shift is taking place. So 1 hydrogen shift is taking place, hydride shift. Now in this case also if you see 1 hydrogen is present, this is carbon number 1, this is carbon number 2, and on carbon number 2 hydrogen is present and 2 methyl group is present, and we have seen that migrating aptitude of hydrogen is more than methyl group. So hydrogen will migrate on this carbon and carbocation form will be this, and you see number of alpha hydrogen in this carbon will be 3, 3, 6, 8, and here it is 4 only. So definitely this is more stable. So rearrangement of carbocation will take place. How many 1 to shift is taking place in this case? Only 1 to shift. So only 1 hydride shift is taking place. Now see question number 7. So if we see question number 7, number of alpha hydrogen in this case is 4 here. Now if this is carbon number 1 and this is carbon number 2. Now on this side on this carbon hydrogens are present, 2 hydrogen and 1 methyl group is present. So hydrogen has more magnetic aptitude, so hydrogen will move here. So if hydrogen will move here, this carbocation will form. Now if we see this carbocation has alpha hydrogen equal to 5. This is more stable, no? This is very good example. So you are not able to see directly. You have to make the carbocation. You have to do 1 to shift, and after doing 1 to shift, you have to see if it is more stable or less stable. So in this case, it is more stable because of more number of alpha hydrogen. Due to hyperconjugation, this carbocation is more stable. So in this case also, rearrangement will take place, and number of rearrangement is number of 1 to shift is only 1, and hydride shift is taking place. Now if we see in this case, this is also a good example. Now if this is carbon number 1 and this is carbon number 2, on this carbon 2 hydrogen and this large group is present. So hydrogen has more magnetic aptitude. So hydrogen will migrate and carbocation form will be this. Now if you see, now this one becomes carbon number 1 and this one becomes carbon number 2. So again, on this carbon number 2, 1 hydrogen and 2 methyl group are present. So again it will go into the rearrangement to make it more stable carbocation. Rearrangement will occur till it will complete more stable carbocation. So if you see, this hydrogen will come here and carbocation form will be this. So this is the most stable carbocation. In this case, 2 1 to shift is taking place, and both time hydrogen is migrating. So first see this example. Very you have to understand this example. Question number 8. So first between 1 to shift will take place, between this carbon and this carbon rearrangement will take place. Now this carbon becomes 1 and this carbon becomes 2. Now if this positive charge will come here, it will become more stable. So from here hydrogen will migrate here and positive charge will come here. So now this is number of alpha hydrogen equal to 8, and here number of alpha hydrogen equal to 4 only, and here number of alpha hydrogen equal to 2. So we have studied the stability of carbocation. So stability of carbocation will be, this is the most stable, then this, and then this. Now see this one. This is carbon number 1 and this is carbon number 2. Now if you see on the carbon number 2, only methyl group are present. So only if methyl groups are present, then one of them had to migrate, because if methyl group will migrate in this case, carbocation form here, there is no hydrogen present here. So methyl group has to migrate. So carbocation form will be this. Now if you see, this carbocation alpha hydrogen equal to 0 and here alpha hydrogen is equal to 8. So this is very, very stable now. So in this case 1 to shift will take place and and in this case methyl group is migrating. Now see this example. If this is carbon number 1, this is carbon number 2. So on this carbon, this two methyl groups and one ethyl group is present. So which group will migrate? See this carbon, this carbocation is very less stable because number of alpha hydrogen is 0. So it will rearrange itself to gain a stability. Now which group will migrate between methyl group and ethyl group? So you have seen that if alkyl group has more number of, if alkyl group has larger alkyl group migrate first in compared to a smaller alkyl group. So this alkyl group is larger. Ethyl is larger than methyl. So it will migrate and product form will be this. So here positive charge will come. In this case alpha hydrogen is equal to 8 and in this case alpha hydrogen equal to 0. So this is very important. If alkyl groups are there, so larger alkyl group migrate first in compared to a smaller alkyl group. Larger alkyl group has more migrating aptitude. Now see this question. In this case also, in this question also alpha hydrogen equal to 0. And now we have three phenyl group on this carbon. This is carbon number 1, this is carbon number 2. So one phenyl group will migrate and product form will be this PH. Now this positive charge here is resonance stabilized plus and here alpha hydrogen is also equal to 2. This is more stable, so this will also go into rearrangement. So how many hydride shift is, how many 1, 2 shift is taking place in this case? Only one, and phenyl is migrating. Now see this case. In this case also alpha hydrogen is equal to 0. If this is carbon number 1 and this is carbon number 2. Now any one of this group will migrate and product form will be this. Now you have studied sigma resonance. Cyclopropyl methyl carbocation goes into sigma resonance. This one is here stabilized by sigma resonance. Sigma resonance. So in this case also rearrangement will take place and 1, 2 shift is taking place, and which is migrating in this case? Cyclopropyl methyl carbocation. Now see this example. If this is carbon number 1, so you have two carbons where migration can take place, where this carbocation can rearrange. So this is 1, this is 2. For this carbon, this is 2 and this is 2. Now where it will migrate? See, if it will migrate here 2 alpha hydrogen is present with respect to this carbocation, and if it will migrate on this carbocation, on this carbon, so product form will be this. Now we see number of alpha hydrogen. Here number of alpha hydrogen is equal to 2, and here number of alpha hydrogen is equal to 6, 10. So this is very, very stable. On this carbon there is no hydrogen. So between two methyl group, one other methyl group will migrate. So if one methyl group will migrate here, so this is the carbocation we will get after rearrangement. And this carbocation has 10 alpha hydrogen. So this is very, very stable. So in this case also, one methyl shift is taking place. Methyl will shift. Now tell me, in this case, rearrangement will take place or not? Now this is carbon number 1, this is carbon number 2. So here one hydrogen is present. So this hydrogen will shift on this carbon and product form will be this. Now in this case alpha hydrogen will be equal to 7. Here alpha hydrogen equal to 1. Definitely this is more stable. So in this case also rearrangement will take place and hydride is shifting in this case. Now tell me in this case, here one methyl group is present and one ethyl group is present. So which group will shift? Larger group will shift. This is carbon number 1, this is carbon number 2. on carbon number 2, one methyl group is present and one ethyl group is present. So we have seen the migrating amplitude. In migrating amplitude, ethyl group has more migrating amplitude than methyl group. So ethyl group will shift. In this case, alpha hydrogen equal to 6, and here alpha hydrogen equal to 2. So this is more stable. So 1 2 shift will take place, and the group which is shifting is ethyl. Now tell me, in this case, where this position will shift? It will, with respect to this carbon, there are two positions where this carbocation can rearrange itself. So where it will rearrange itself? So if you see, on this carbon, one methyl group is present and one hydrogen group is present. Now on this carbon, one methyl and one ethyl group is present. So we'll do both shifting and see where it is more stable. So if we are shifting on this carbon, if you are rearranging this carbocation with this carbon, so ethyl shift will take place. So here we will do ethyl shift. So if you are doing ethyl shift, carbocation will form this one. Now one more case is there. If you rearrange carbocation with this carbon, so in this case a hydrogen shift will take place. Hydrogen will shift and product form will be this. Now in this case, if you see, in this case alpha hydrogen is 3 to 5, 3, 3, 6 and 7. And in this case, if alpha hydrogen, it will count 3. Okay, here it is 3 to 5, 6, and here we count alpha hydrogen, that is equal to 7. Now this has more number of alpha hydrogen, so this will be more stable, na? So this is the correct rearrangement. This one is correct and this one is wrong. This rearrangement will not take place, because if this carbocation will rearrange with this carbon, with if hydride shift is taking place, then more stable carbocation is forming. That's why this is the correct one and this is the wrong one. In this case, this will not take place, and this hydride shift will take place. Now I will give you some more questions. Okay, do these questions. Now tell me, in this case, if this is carbon number 1 and this is carbon number 2, so if hydride shift is taking place, if 1, 2 shift is taking place, this carbocation will form. Now this is alpha, in this case alpha hydrogen is equal to 4, and in this case also alpha hydrogen is equal to 4. Now if you see the stability order of carbocation, so we will see, okay, this is more stable than this one, but hydride shift will rearrangement will not take place in this case, because we do not consider, whenever we consider rearrangement now, we do not consider a stability due to plus I effect. So during rearrangement, a stability due to plus I effect, only we will consider if a stability due to hyperconjugation and resonance is taking place. Here alpha hydrogen is same, there is no resonance in both the cases. So we do not consider stability due to plus I effect during rearrangement. So stability due to plus I effect ignored during rearrangement. We will only consider stability due to hyperconjugation and resonance. In this case, we will see this carbocation is more stable due to plus I effect, but we do not consider a stability due to plus I effect during rearrangement. Now, see in this case, if this is carbon number 1, this is carbon number 2. So in this case, rearrangement will take place because here positive will come, and here alpha hydrogen is equal to 7, and here alpha hydrogen is equal to 3 only. So this is more stable due to hyperconjugation. That's why in this case rearrangement will take place, and here no rearrangement will take place. So 1, 1, 2 shift is taking place, and hydrogen is migrating. Now in this case also, this is already most stable carbocation, so no rearrangement will take place. Now see this case. Now if you see, this is carbon number 1 and this is carbon number 2. So both have same number of alpha hydrogen. This will not take place. So both have same number of alpha hydrogen. See, positive will come here after doing hydride shift. So here it is minus I effect. So you see this is less stable, so this cannot take place. No rearrangement possible in this case. Now see this example. Now in this case, this has alpha hydrogen equal to 4. Now this is carbon number 1 and this is carbon number 2. So we move this, if this positive charge rearrange itself to here. So now if you see in this case alpha hydrogen equal to 2 only. But this oxygen has lone pair, and due to this lone pair and this carbocation has vacant p orbital, so back bonding will take place, and due to back bonding this will be more stable than this one. So rearrangement will take place in this case due to back bonding. So in this case carbocation is gaining a stability. In whole organic chemistry, whenever positive charge is present near lone pair, then that is the most stable carbocation. Understand? So carbocation is stable due to back bonding in this case. So in whole organic chemistry, whenever carbocation is present near lone pair, that is the most stable carbocation because of back bonding. So here rearrangement will take place. See, this is alpha hydrogen equal to 4 and this is alpha hydrogen equal to 2, but still rearrangement will take place because this carbocation is more stable than this carbocation due to back bonding. Similarly in this case, no rearrangement will take place. This carbocation is already stable due to back bonding, so no rearrangement. Now in this case, see how many rearrangement will take place in this case. You have to see how many rearrangement will take place. This is carbon number 1 and this is carbon number 2. So here one hydrogen is present. So one hydride shift will take place from here, and shift will take place, and carbocation form will be this. This will be carbocation form. Now if you see this, now this is carbon number 1 and this is carbon number 2. So on this two hydrogens are present. So hydride shift will take place. If hydride shift will take place, this carbocation form. Now in this case we see alpha hydrogen equal to, in this case alpha hydrogen equal to 7 and here alpha hydrogen equal to 1. But again this carbocation is back bonding stabilized. This carbon is vacant p orbital and this oxygen has lone pair. So lone pair donates its oxygen will donate its lone pair to vacant p orbital of carbon. So this is back bonding stabilized. That's why this is the most stable carbocation. This is back bonding stabilized. So how many 1,2 shift is taking place in this case? 2 1,2 shift is taking place, and in both the cases hydride is shifting. Now see in this case, okay, here positive charge is present here. Here positive charge is present here. Okay. Now this is carbon number 1 and this is carbon number 2. So on this carbon hydride shift will take place. So this product will form. So now this become carbon number 1 and this become carbon number 2. So again all three are ethyl group. So here hydride shift is taking place. S shift. Now in this case ethyl shift will take place. On carbon number 2 ethyl shift are present. Ethyls are present. So ethyl shift will take place and product will be like this. Now here positive charge will come. Now if we see, this is very important example. How many 1,2 shift will take place in this case? Now if you see, this is carbon number 1 and this will become carbon number 2 and here hydrogen is present. So in this case hydride shift will take place. Now and here positive will come. So we count number of alpha hydrogen in this case. Number of alpha hydrogen is 2, 4 and 5. And if you count alpha with hydrogen in this case, that will be 3, 3, 6 and 7. So this is more stable carbocation. No? So this will be the final product in this case. Very important one. So there are 3 1,2 shift is taking place. Now this one, this is 1 and this is 2. So larger group will shift. Tertiary butyl is there. So that has more magnetic aptitude. So product form will be this one. This is the product. Now in this case again, if this is here positive charge will one is current. Okay, in this case there will be no shift taking place. Already it has more stabilized. So in this case no rearrangement will take place. No rearrangement. Okay, see this example, very important. Here the CH3 group is fixed and positive charge is present here. Now we know this. In this case, this is carbon number 1 and this is carbon number 2. On this carbon number 2, this is the large group, so this will migrate. So product form will be this. So there will be no change in configuration in this case. Configuration will remain same to same because this bond is migrating. This is migrating here to here. So here, if this is CH3 is in wedge position, so hydrogen will be on dash position. There will be no change in configuration because if we draw transition state, so transition state for this will be like this. This bond is breaking and it's connecting to this carbon, and this is the transition state. There is nothing to do with this carbon. There is nothing to do with this carbon configuration. Understand? There will be no change in configuration. So you can write in 2 points in notes. First one is a rearrangement is completely intramolecular process. Rearrangement is intramolecular process. And second, there will be no change in configuration. Second, during rearrangement there will be no change in configuration. Now example number 26. And 27. So these two examples are connected with each other. Now here we take two cases. See, if in this case we are doing methyl shift, first we will do methyl shift. So if we are doing methyl shifting, product form will be this. And suppose this is P, this carbocation is P. Now we will do phenyl shift. If we do phenyl shift, product form will be this pH. Now if you see in this case number of alpha hydrogen that is equal to 4, and it's also resonance stabilized. This carbocation is alpha hydrogen, 4 alpha hydrogen is present, and it's also resonance stabilized. Sorry, 5 alpha hydrogens are present and resonance plus R effect is also there due to this phenyl group. Now we see in this case alpha hydrogen equal to 8, but there is no resonance. So in this case, a stability order of carbocation is, this is Q and this is R. So P will be more, Q will be very stable because of hyperconjugation as well as plus R. Then R, then it will become P. So this is the stability order in this case. So now this is more stable. So in this case methyl shift will take place. This will not take place. But I have given you order that first if alkyl group is present and aromatic compound is present, so aromatic group will migrate. So when this aromatic group will migrate, that case we will see here. So in this case, if you see, now in this case, first do methyl shift. If we do methyl shifting in this case, product form will be this pH, OH, and Me, and positive charge will come here. Now if we do phenyl shift, product form will be this Me, OH, and here will be pH and positive charge will come. Now if this is, you take this as P dash, and this is Q dash, and this is R dash. Now you see, if you see the stability order, will get the same. Q dash will be more stable than R dash, and then it will come P dash. Now, in these two cases, why this carbocation is stable? What is the main reason for stability of carbocation? So, in Q dash and R dash, main reason for stability of carbocation is back bonding. So, they are more stable due to back bonding. Here, due to phenyl, there is some plus R effect. But more reason for stability is back bonding. It has lone pair available, so it will be more stable due to the back bonding through the lone pair of oxygen. So Q dash and R dash will have similar stability. Q dash will be slightly higher stable, but they will have similar stability. Now in this case, methyl shift will not take place. In this case, we will take phenyl shift. Phenyl shift will take place in this case. So in this case, main reason for stability is back bonding. Main reason for stability is back bonding. Now we have a study that migrating aptitude order is hydride, then aromatic, and then alkyl group. Now when to follow this migrating aptitude? So we have to follow this migrating aptitude when product form is stabilized by, when carbocation form is stabilized by back bonding. So now in this case we have to do phenyl shift. This is wrong, and here this is wrong, because in this case it is not stabilized by back bonding. So we have to see the most stable carbocation. So when product form, when carbocation form is stabilized by back bonding, then we have to follow migrating aptitude order. Migrating aptitude order. If not, then you have to make the most stable carbocation. If it is not stabilized by back bonding, then you have to make the more stable carbocation. If it is not stabilized by back bonding, try to obtain most stable carbocation. I hope you understand when to do methyl shift and when to do phenyl shift, when you have to do alkyl shift and when you have to do phenyl shift. So when carbocation is stabilized by back bonding, then only will follow migrating aptitude order. If not, then you have to obtain most stable carbocation. It does not matter. We can move phenyl also and we can move methyl also. If after shifting phenyl we are getting more stable carbocation, then we will shift phenyl. Understand? So if it is not stabilized by back bonding, then try to obtain most stable carbocation. I will give you one example. 28. Now to tell how many hydride shift will take place and to draw the correct product. So first here 1, 2 hydride shift will take place. This is carbon number 1 and this is carbon number 2. So this product will form. Now in this case, if this is carbon number 1 and this is carbon number 2, so we have two possibilities. We can do methyl shift also, and we can do phenyl shift also. So if we do methyl shift, product form will be this pH. Here Ne will come. Here positive will come. Now if we do phenyl shift, product form will be this. Now this is resonance stabilized. And this is not getting stable by any back bonding. So this shift is wrong. We will do methyl shift only because this is more stable carbocation. If carbocation is not stabilized by back bonding, then we will form that carbocation which is more stable. Now in this case, this is the most stable carbocation. So we will form this carbocation. Now this carbocation pH positive charge, here Me and here pH. Now in this case, if this carbocation will come here, it is getting stabilized by back bonding. So here phenyl shift will take place. In this case, phenyl shift will take place, not methyl shift. Because when this carbocation is coming here, it is getting stabilized by back bonding due to the lone pair of oxygen. So phenyl shift will take place, and final product will be this. Here positive electron and methyl. This is the final product. So write down. So question number 29. See, in this case, rearrangement will take place or not. This positive charge is present on double bond. So no rearrangement. You can write positive charge present on double bond and triple bond. Positive charge present on double bond and triple bond do not involve in rearrangement. Present on double and triple bond do not go through rearrangement. Do not involve in rearrangement. Now let's study ring expansion. Next topic is ring expansion. This is the part of rearrangement only. Ring expansion. Now I will give you one example. Now if this is carbon number 1, this is carbon number 2. Now on this carbon, on carbon number 2, we have this one hydrogen is present and these two groups are present. These two groups are present on this carbon, one hydrogen, and these two groups are present. Now, if you shift hydrogen, after shifting hydrogen, on doing hydride shift, on doing H shift, we will get this thing. So, now in this case, alpha hydrogen is equal to 3, 2, 5, 7. Now, we can also do from anyone from these two bonds, we can shift this bond to here. So with this bond to here, it will be like this. Transition state form will be like this. This will be transition state, and positive charge will come here. So we are shifting this bond. This is the transition state. So product form will be like this. This is nothing but 5 km. This is the product. Now which is correct between these two? In this case, number of alpha hydrogen is equal to 7, and in this case, number of alpha hydrogen is equal to 4. But we have a studied Bayer's strength theory. So if you see the angle strength, so if you see angle strength in this case, so in this case, like this carbon is sp3 hybridized. Now for sp3 hybridized, angle should be 109 degree, but here angle is 90 degree. So angle strength in this case will be 109.28 minus 90 degree, that is 19.28 degree. Now in this case, if we see angle strength, now this carbon is sp2 hybridized, and in this case angle is 90 degree. So in this case, angle strength is 120 minus 90, that is 30 degree. Now we check angle strength in this case. So angle strength in this case will be okay. This carbon is sp2 hybridized, so its angle will be 120 degree, and in the case of 5 ring, angle will be 108 degree. This is 12 degree. So we see this one is getting more stabilized due to angle strength. It is getting more stabilized due to less angle strength on doing ring expansion. So this shift will not take place because in this case there is high angle strength. There is 30 degree angle strength, and here angle strength is 12 degree only. So ring, in this case, this is the correct product. This ring expansion will take place. So 4 member ring will convert into 5 member ring on doing 1-2 shifting. There is also 1-2 shift. So you can write 2 points in note. First is ring expansion take place. There is also 1-2 shift. And second, ring expansion take place due to relief in angle strength. Ring expansion takes place due to relief in angle strength. Now I am giving some examples and to tell if ring expansion will take place or in this case or not. Second example. See here positive charge is there. So first we do, this is 1 and this is 2. So it will give this. Now this will become 1 and this will 2. Now on this hydrogen, on this carbon, one hydrogen is present and these two groups are present. So if we do ring expansion in this case, so this product will form. This is a transition state. So this will convert into 6 member ring. So it will convert into 6 member ring. This will shift here and it will convert into 6 member ring. Now in this case it is more stable due to relief in angle strength. This is the final product in this case. This is the most stable carbocation form after all the rearrangement. So ring expansion will take place in this case also. Third example. Now this is carbon number 1 and this is carbon number 2. Ring expansion will take place in this case also. Now any one of these two can migrate. This will migrate here. So ring expansion will take place. Now how can you number this? Suppose this is 1, 2. So this will become 1, this will become 2, this will become 3, 4, 5, 6. So where it is connected? This is 1. Now this is moving 2, 3, 4, 5, 6. This is the way of numbering after forming the product. Now in this case also, this is 1, this is 2. So if we do the ring expansion, this bond will shift here. This is the transition state. This bond will shift here. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6. So we draw the product. Product will be like this. First, methyl group is present in 3. Suppose this is positive charge present here, and this is 1. This will be 2, this will be 3, this will be 4, this will be 5, this will be 6. So one methyl group is present here, and one methyl group is present here. So you can draw like this. You can do the numbering like this: 1, 2, 3, 4, 5, 6. So if I do 1, okay. Positive charge will come on second carbon. So positive charge will present here. This will be 1, 2, 3, 4, 5, 6. And here also positive will come on second carbon. So this will be the product. This is the final product. Now fourth example. This is fourth one, very important. Now this will also go into ring expansion. This is carbon number 1, this is 2. Now between these two groups, between this group and this group, which will go into the which will migrate between these two groups. So I have said that in alkyl group, which group will migrate? Which is large size, which is large in size. This group is large in size, so this group will migrate. So if we migrate this group, product form will be, first draw the transition state. This is the transition state. This is carbon number 1, this is carbon number 2, 3, 4, 5 and 6. So positive charge will come on carbon number 2. This is 1, 2, 3, 4, 5, 6. So positive charge will come on 2 and methyl group will come on 6. So this is the product. Question number 5 in the ring expansion. And here positive charge is present. So what will happen in this case? See, now this is carbon number 1 and this is carbon number 2. So now this will shift. This shift will take place. In this case also ring expansion will take place. This 4-membered link will expand into 5-membered link. So see how this will take place. So we draw the transition state. So this bond will break from here and this bond will go to here. This bond will break from here and will connect with this one. So positive will come here. This is carbon number 1 and this is carbon number 2. So product form will be like this. This is the product form. 2 5-member ring will form and positive will be here. So there is 1 2 shift 10 place. Now 6th question, very important. You have to tell me how many 1 2 shift will take place in this case. Positive charge is present on this methyl group. Now this is carbon number 1 and this is carbon number 2. So on carbon number 2, one hydrogen is present, but that hydrogen will not shift because ring expansion will take place. After ring expansion, it will have relief in angular state. So ring expansion will take place, and this methyl group will shift here. So first product will be like this. This will the product will get. Here positive will come here. Ring expansion is taking place. See. What is the transition state in this case? This bond will shift here. This bond will shift here and 5-member ring will be formed. This will be the transition state. And positive will present on the second carbon. This is the first carbon, this is the second carbon. So this is the product we will get. Again, in this case, if you see, this become first carbon, and this will become second carbon. So again, ring expansion will take place. So on doing expansion, product form will be this. This 5-member ring will combine into 6-member ring. So one more 1 2 shift will take place. And in this case, this bond will shift here, and it will shift here. Positive will come on the second carbon. So product form will be like this. 5-member ring will convert into 6-member ring. This is the product we will get, and here positive will come. So 1 2 3 4 5 6. So this is the final product we will get. There are 3 1 2 shift is taking place in this case. So whenever there is possibility of ring expansion, we have to do the ring expansion to decrease the angular strain in the compound. So this is the final product we will get in this case. So this carbon, this bond will go here, this bond will go here, and product form will be this. And positive charge will come on this carbon. Now again, if we take this as 1 and this as 2, so again this 5-member ring will convert into 6-member ring. So final product form will be this. This is the final product, and positive will come on this carbon. Now question number. Now we'll see the ring expansion in more than, like here we have seen the ring expansion only when 3-member ring is converted into 4-member ring, 4-member ring is converted into 6-member ring. One more example, important example, that this will go into ring expansion or not. Now this is cyclopropyl methyl carbocation, cyclopropyl methyl carbocation. And this is very stable due to sigma resonance, you know this. But when we do the ring expansion, on doing the ring expansion, we will get the cyclobutyl carbocation, and this will be stable due to less angular strength. This will form, but it will be in equilibrium with each other, and percentage of cyclopropyl methyl carbocation will be greater than cyclobutyl carbocation. Now we will see the ring expansion in the case of more than 6 membered carbon. Ring expansion having more than 6 number of carbon in the ring, having 6 or more than 6 membered, more than 6 carbon in ring. So first example I will take cyclohexane. Now here position is present. Now two cases is there. If we do, here hydrogen is present. So if we do hydride shift, so product form will be this. In this case, alpha hydrogen is equal to 7. Now if you do the ring expansion, product form will be this. And we know that 7-membered ring has more angular strength than 6-membered ring. So this is the unstable. So in the case of 6-membered ring, this will not the product. Now again, we will take one more example. In this case, this is correct. Now we are taking this one. CH3 is present here and polyester is here. Again, two cases is possible. First we do hydride shift, and second we do ring expansion. So if we do hydride shift, this product will form. Okay, in this case there is no hydrogen, so we do methyl shift. So here we do methyl shift. So on doing methyl shift, product form will be this. This is the product. And if we do the ring expansion, so for ring expansion this is 1, so this is 2. So for ring expansion this will the product. Now again, this is the wrong product, this is the correct one. In this case also ring expansion will not take place. So when in the case of 6-membered ring expansion will take place, that case we will see. 10th example, very important. When in the case of carbon having more than 6-membered ring expansion will take place. So see this example. Here we have OH and positive charge. Now if we do ring expansion in this case, this product will form, and here OH will be there and positive charge will come here. If we do the ring expansion, so if we are doing ring expansion in this case, this bond will move here. So instead of here, this bond will break and it will move here, and OH is present here. So positive charge will come. This is carbon number 1, this is carbon number 2, this is carbon number 1, this is carbon number 2. So positive charge will present on carbon number 2, and it is getting stabilized by back bonding. So only in the case when ring is getting stabilized by, when doing ring expansion, ring is getting stabilized by back bonding, then only we do the ring expansion. So only in this case, when after doing ring expansion, carbocation are getting stabilized by carbocation is getting stabilized by back bonding. Then in that case only we can do the ring expansion. Then in this case only we can do ring expansion having more than 6 carbon. We can do ring expansion having more than 6 carbon. Ring expansion having more than 6 carbon. So when we will do the ring expansion, in the case of 6-member ring, 7-member ring and 8-member ring, when after expanding the ring, carbocation is getting stabilized by back bonding. So next example, see this one, 11th one. This is 7-member ring. Now this is OH and this is positive charge. So in this case also ring expansion will take place. This is carbon number 1, this is carbon number 2. And we will convert into 8-member ring because here also carbocation form is getting stabilized by back bonding. So product form will be like this. Now last topic, we will study ring contraction. Ring contraction. So first example I will take. See here OH is there and here positive charge is there. Now if you see, if this is carbon number 1 and this is carbon number 2, so on this carbon number 2, ethyl shift will take place and product form will be this. Now this carbocation is more stable due to back bonding. Now similarly, I will take one more example. You can see the similarity between these two examples. Now here OH is present and here positive charge is present. Now if we join this, in this case if we join these two, it is becoming 6-member ring and one is becoming 5-member ring. Now here also you have to see the same cases. Now this positive charge is present here. This is carbon number 1 and this is carbon number 2. And we know that whenever positive charge is present, whenever carbocation is present near back bonding, near the lone pair, then that will be the most stable carbocation. So again in this case also, now this is carbon number 2. So if this positive charge will come here, this will become more stable carbocation. So how it will come here? You have to do some shifting. So which bond will shift? So if you shift this bond, then it will form compound form will be like this. So this 5-member ring will form and positive charge will come here and here. Now this positive charge is stabilized by back bonding. So in this case, whenever more stable carbocation will form, that only due to back bonding, then ring contraction will take place. I hope you understand the similarity between these two examples. Here we are doing ethyl shifting because see here we are doing ring contraction because when positive charge, when carbocation is forming here, it is getting stabilized by back bonding. That's why ring contraction is taking place. Now second example. Again this is also 1-2 shift and you have to see we have to form a more stable carbocation. This is the second example. Now you tell me in this case ring contraction will take place or not. Here positive charge is present. So this is carbon number 1 and this is carbon number 2. So ring contraction will take place because if this positive charge will come on this carbon, then it will be more stable due to back bonding. Now which ring will contract? 6-member ring or 5-member ring? See, now if you see on this carbon, this side this group is present and this side this group is present. And you have said, like I have told you, that migratory aptitude of large group is more than a small alkyl group. So this group will migrate. Or you can also think that if 5-member ring will convert into 4-member ring, there will be very high angle of strength. But if 6-member ring will convert into 5-member ring, there will be less angle of strength. So in this case, 6-member ring will contract into 5-member ring and product form will be this. This will be OH and positive will come here. This will be the product. Third one. We know that this has very high angle strength. So this will also go into the ring contraction. This is carbon number 1, this is carbon number 2. So this will shift here and will convert into this. And this carbocation is stabilized by sigma resonance. So 4-member ring, 4-member cyclobutyl carbocation convert into cyclopropyl methyl carbocation. Now fourth example. Now you know that like this is carbon number 1 and this is carbon number 2. We know that 7-member ring is less stable than 6-member ring. So if this shift, this bond will shift here. This bond will shift here. 6-member ring will form, and if this is and positive will come on the carbon number 2. This is carbon number 1. So this is carbon number 1, 2, 1, 2, 3, 4, 5, 6, 7. So positive charge will come on carbon number 2. So this is the product. Now fifth one. And positive charge is present here. So in this case ring contraction will take place or not? Ring contraction will take place because this is unstable. Now see, this is carbon number 1 and this is carbon number 2. So methyl shift will not take place. Ring contraction will take place from this carbon number 2. This bond will move here. So if this bond will move here, product form will be this. This bond is moving here. So carbon number 1, 2. It will be like 1, then this will become 2 and positive will come here. So this will be product 1, this will be 2. Now this is 1 and this is 2. So this will be the final product in this case. So that's it for today's lecture. Thank you.